Hello, this is a video on writing Lewis structures for molecules, and today we're going to write those Lewis structures for single bonds. So reading through these steps. Step 1, count the valence electrons on all the atoms. Number 2, draw a structure of the atoms with the central atom either being carbon or the more positive least electronegative atom. And if you have multiple carbons, it's going to be a carbon chain. I forgot to write that in there, but I said it nonetheless. Number 3, add electrons in single bonds with a line, and then lone pairs, two dots around each atom to form the octet. There are known exceptions. Hydrogen has 2, beryllium has 4, boron, aluminum have 6, and if there's 5 or 6 bonded pairs, we'll talk about the expanded octets with the trigonal bipyramidal and octahedral shapes. So today, when we do that, if the electron counts match, this is the Lewis structure. So using single bonds, this will be the Lewis structure. In the next video, we'll talk about double bonds, double and triple bonds to get the octet. So we're going to write simple molecules today. So the first one is going to be methane, number 2 ammonia, number 3 water, number 4 HF, and number 5 F2. So we'll start with CH4. So counting my electrons, each carbon has 4 valence electrons. The electron configuration is 2s2p2, and the valence electrons are in the s and p orbitals. And then each hydrogen has 1, so 4 plus 4 is 8. Well, you can see where we're going to get the octet. So I'm going to draw my carbon, and I'm going to draw 4 hydrogens around the carbon. Draw a single line between them. That's not very good. So I can use my cool erasing Apple pencil, and I will draw a better H bond, CH bond there. So there are 4 CH bonds. 4 times 2 is 8 electrons. We make the octet. Number 2 is going to be NH3. So each N has 5 valence electrons. Each hydrogen has 1. 3 times 1 is 3 plus 5 is 8. Golly gee, we're going to draw 3 H bonds around them. And then in the fourth electron pair is not going to be a line, it's going to be 2 dots. So there we go. There's our lone pair. And you'll see the models of those in real life in the next part of this video. Also, 8 electrons will make the octet. Number 3 is going to be H2O. That's some high quality H2O right there. So there's 2 times 1 plus 6, which is going to be 8. So again, I'm going to draw an H, O, H, and then I'll draw 2 lone pairs, and I can draw it like this as well. Now you're like, well, which one is it? Is it this one or this one? When you draw it in 3D, later in the video, you'll see that the water molecule is bent. So that's a little bit more accurate. But if you rotate it in space, then you could see like the HOH head on, and you'll see the model in a little bit, okay? It's hard to draw a 3D item in a two-dimensional iPad. Okay, the molecule number 4 is HF. The H has 1, the F has 7 for a total of 8. So again, we're going to draw the F, and there's 1 H, which means the F has to have 3 lone pairs around it. And why does the H not have any lone pairs? Because H is on the first energy level, we're only allowed the s orbital, and there's the 2 electrons in the s orbital. So HF, 1 bond, 3 lone pairs around the F. And then molecule number 5 is F2. Diatomic fluorine is going to be a single bond. You may say, why didn't you start with oxygen and nitrogen? Because they're going to be double and triple bonds, you'll see in the next video. So if you draw the F together, 2 times 7 is 14. And you may say to yourself, the octet is 8 times 2 is 16. But we're not having them all on their own. This pair of electrons is going to be shared. 2, 4, 6, 8, 10, 12, 14. So we have 3 lone pairs, 3 lone pairs, 2, 4, 6, 8, 10, 12, 14, 2, 4, 6, 8, 10, 12, 14. So the F2 molecule has 7 valence electrons each atom, sharing 2 in the middle for 14. And that's our Lewis structures. Now we'll scroll down and look at the molecular shapes. And there they are. Next video.
The Lewis structures for methane, ammonia, water, hydrogen fluoride, and diatomic fluorine. So here's the Lewis structures. Notice there's dots and there's lines, and then in a 3D model, when we do VSEPR VSEPR theory, it appears at first glance that CH4 is going to be at 90-degree angles, but in 3 dimensions, at 360. And some of you, if you're at school, will be using these models. If you're at home, what you can do is get some marshmallows and some toothpicks, and you can make your own models if you so desire. And if you're working by yourself and you touch them on with your hands, you can eat the product. The marshmallows, not the toothpick, that is. So this is a methane molecule, CH4, and later we'll learn that it's an sp3 hybrid. Because all of the bonds are equal all the way around, it's a non-polar molecule. And we'll learn more about that later. Ammonia, all you do is you pop one of the H's off, and you have NH3. Notice this model, the way this model works is these are bonded to hydrogen, so they're called localized electrons because they're local to that bond. But this is a lone pair. It's called a sp3 hybrid because there's 4 areas of charge density, 3 bonds, and 1 lone pair. So it's still an sp3 hybrid. Scroll down to water. Pull off one of the H's. Now we have H2O. And notice we have 2 bonds and 2 lone pairs. There's still 4 areas of charge density, so it's still an sp3 hybrid, but there's 2 bonds and 2 lone pairs for a total of 4. And that's the octet. That's where we get it. And notice that, let me put the molecules back together. CH4 methane has 4 bonds, and it's at a 109.5 bond angle. I'll prove that later with vectors. Okay, when I have a space in VSEPR theory, it squishes that 109 down to 107. And then water is down to 104.5 or 104 or 105. You know, what's a half a degree? You can't measure that. But I love these model kits because it shows the bonded pairs, the lone pairs, and it shows the geometry with the right angles, with the correct angles, the correct angles. Let me scroll up to hydrogen fluoride. We have a fluorine with 1 bond and 3 lone pairs and 1 H over here. And because this fluorine still has 3 lone pairs and 1 bond, it's still an sp3 hybrid. And all the first row, CONF, they all make the octet. Once you go past those, we'll talk about the expanded octet later. Okay, diatomic fluorine, F2. See, there's each F has 7 electrons, but when you share the 2 in between, there's 3 lone pairs, and 1 bonded pair for a total of 14 electrons in the Lewis structure. So it's also, let me go over here. Molecule is not the same electronegativities. Polar toward the F is the higher electronegativity. Okay, this molecule is nonpolar, so fluorine is a gas. We'll talk more about how polarity affects intramolecular forces and boiling points of liquids and gases. Okay, down here below is the exceptions to the octet. BeCl2, BH3, and BF3. Beryllium is stable. When I say happy, it means it makes stable molecules. And personally, I've never seen BeCl2. I've never seen any in a test tube or a beaker, so I can't personally say this, but according to books, BeCl2 is a compound. Okay, BH3 borane, I've heard about and seen diborane, B2H6, but I can't remember seeing borane personally. I've seen boric acid, they use it to kill spiders and such. And BF3, boron trifluoride, has 3 bonds, but no lone pair. So the BF3, it'll be a trigonal planar. We'll look at the VSEPR shapes in a moment. Here's the expanded octet. Phosphorus and sulfur have the d orbitals available because it's on the 3rd level. On the 1st level, the s orbitals, 2nd level s and p, 3rd level sp and d. Even though the phosphorus and sulfur are not filling the d orbitals, they have them available according to quantum theory and quantum numbers. So you can have the expanded octet, 10 electrons around PCl5 and sulfur hexafluoride SF6. I have personally never breathed in sulfur hexafluoride. However, I've seen videos where they breathe it in and they sound like really deep voice. So there's probably a link to the Steve Spangler video where there's an SF6. I have that link for my gas laws later, so I'll make that link in there. Okay, now you do these molecules: PCl3, H2S, CCl4, and C2H6. Bye.